Please also confirm that you can see the presentation.
Yes, sir.
Thank you. Okay. Sorry, just a minute. So it seems somebody hasn't muted the mic. Please just check. Please just check. Somebody hasn't muted the mic. Okay. So let us begin the discussion. This was the point where we ended the last class on solenoidal and irrotational fields. Irrotational fields. Spelling mistake here. Anyway, so let's look at the technical part of the discussion. Have you all muted the mic, please? Just check. Okay, so for a solenoidal field, you have zero divergence, as has been written there. We shall just, today in this little discussion, we shall try to gain a geometrical impression of what happens in a solenoidal field by applying the ideas we have gathered from the vector integral theorems. So here's the Gauss divergence theorem, divergence of A. You take the volume integral of that, and it's going to be the closed surface integral of the, closed surface flux, actually. Okay, so if for a solenoidal field the divergence of A is 0, then the total flux will also be equal to 0. So here I have written something. Let me first read it out, and then we shall look at its explanation. For a solenoidal field, any closed surface will have an even number of field lines intersecting it. So here's the closed surface. Here you have the closed surface, and the solenoidal field lines are like this. So try to understand this point carefully, that either a particular field line will not cross the closed surface at all. This rough, uneven figure is the closed surface. It doesn't have to have any symmetric geometrical shape. So a field line may not cross the surface at all, or if it has to cross, it will do so an even number of times. So here let us try to see. The field line enters here, and then it exits here. So an even number. Then it again enters here, and it exits here. So you will see that there's the number of entry and exit will be some multiple of 2. So it is an even number. So every time a field line enters and exits, it will contribute no flux at all. Here's an inward going flux, but then it's also coming out. And as a result, the net flux will be 0. So that is the basic geometric idea of a solenoidal field, that it has got 0 flux when you have divergence of A is equal to 0. So that is one idea of a solenoidal field. There's another thing about irrotational field. Once again, I stress that there's a spelling mistake over here, irrotational fields. So here, one last point I shall make on this discussion. In the last class, we hurried. I did not want to hurry through this discussion, but this is a particularly important discussion. This last point, that if you have an irrotational field, then of course, the signature of that field is that its curl will be zero. So zero curl field, irrotational field. Curl of A dot dA, A dot dl, cyclic integral. This is Stokes's integral theorem. So the Stokes integral theorem, if you apply the curl of A equal to zero condition, then that will make the loop integral, closed loop integral, to vanish. Because if the curl of A is vanishing on the left-hand side, the left hand is equal to zero. If the left hand is equal to zero, then the closed loop integral on the right-hand side will also be equal to zero. Okay. Now, let us look at the consequence of that. This P is supposed to be perimeter. Many authors use it, many don't. So here I've just used it. So this is S as in surface, this is P as in perimeter, this is V as in volume, and S as in surface. Volume to surface, the divergence integral, and surface to perimeter, or the boundary line, the curl integral. Okay, now let us look at this idea that the closed loop integral vanishes. If it does, then A dot dl, the closed loop integral, will be equal to, let us now try to follow this discussion carefully. You follow this discussion carefully. When you say you have a closed loop integral, it means that you are starting at a point and then you are coming back at that same point. Just a minute, can you please excuse me? Hello? Yes? Can you please call me later? I'm in the middle of a class. I'm sorry. Thank you. Call me after 11:30. Hello. Yes, I hope all of you can hear me. So you start at a point, you go all the way around, like here. You're starting at A. You go all the way around and you come back to A. But you can break this full cycle into two paths. Path, P-A-T-H. A to B, and then from B to A. The closed path, you can break it into, the closed cycle, you can break it into two paths. So that is what I have done. A to B, first you carry out the integral over A to B over path 1. dl, this subscript 1 means that it is a path integral over A to B. And then dl subscript 2, meaning it is over the second path. But for the second path, the starting point is B and the ending point is A. So basically, you have now decomposed the closed loop integral into two path integrals, open path integrals going from A to, not open path integrals, I'm sorry, path integrals with limit, A to B, and then from B to A. Okay. And then what we do is that, look at this integral, this plus this is of course equal to 0 because A dot dl, the overall loop integral, is equal to 0. Okay, so A to B you have one is equal to this, I'm taking to the right hand side, minus A dot dl, you have got 2, B to A. Okay, so B to A to B, B to A with a minus sign. Next is, what we do is that we eliminate the minus sign by exchanging the limits. Instead of writing going from B to A, we are writing it is going from A to B, but then when we exchange the limits, the minus sign goes away. I hope you are aware of this basic idea of definite integrals within limits. So that is what we have done. So if we have done this, then this is the result as written here. In an irrotational field, the line integral is independent of the path. So you can see this is an irrotational field. Curl of that irrotational field vanishes. If that is the case, then here's the proof. Here you have the proof that a line integral from a point A to a point B, from a point A in both sides to point B, except that these two integrals are happening over two different paths. One is from along this path, path 1, as in the subscript 1 in brackets, and this is along path 2, as in the subscript 2 in brackets. So this is an irrotational field. The line integral is independent of the path. And here it is written. An example of that is work done in gravity. I hope you are aware of the fact, as you might have studied in school, that gravitational field, work done in a gravitational field is independent of the path that you take. In a gravitational field, you can travel along any path. I have asked you, you can take a suitcase, heavy suitcase, up the ground floor to an upper floor or to the roof of your house. You can take the stairs. You can carry it up by scaling along the wall. Any way you go, starting from the ground to the roof of your house, whatever be the path that you take, it will not matter. What matters is field. So curl of A is equal to 0. So this idea will be important. Today we have a tutorial at 2 p.m. So remember this idea that whenever you have to check for the line integral of a vector, first you ensure whether the curl of the vector is equal to 0 or not. If it is equal to 0, that makes your task so much easier. Why? Because it doesn't have to follow it doesn't depend on the path that you take. You just have to put the initial values and the final values in the integral and you'll get your answers straight away. But otherwise, you'll have to worry about the equation of the path along which you will have to carry out the integral. Okay, so now I shall stop this discussion, and this was from a supplementary set of notes. As I said, these two ideas required some in-depth discussion, so that is why I thought that I would not hurry through in the last class. There are some errors over here. There's a spelling error here, and there are two vectors missing here. There's a vector sign missing here, and there's a vector sign missing here. I will correct these things, and I shall supply you the notes in due course. Okay, so now let me stop this presentation and get back to the main thread of our discussion. These are all a part of the supplementary set of notes. So here we are. Can you please confirm that you can see the presentation?
Yes, sir.
You can? Thank you very much. Okay. So in the last class, this was the point where we ended, and then we went off to discuss a few things in the supplementary set of notes. So this was the thread of the discussion. So with that, we have fairly well finished the various implications of vector integration. I mean, of course, the subject in its own right is a vast subject, and if one were to study it seriously, even one semester will not be sufficient. But here we have understood only as much of the subject as is necessary for us to proceed with our discussion of electromagnetic theory. So we have finished that part of the discussion, vector differentiation using the Dale operator, and vector integration, vector integral calculus, all these things, the gradient theorem, the Stokes-Curl theorem, the Gauss divergence theorem, and certain implications of vector integral theorems regarding solenoidal and irrotational fields. We have discussed all that. Now, we shall move on to a new mathematical topic, namely that of curvilinear coordinates. Let us try to understand this thing, the curvilinear system of coordinates. So here we are. So far, we have discussed our coordinate system. We have operated under the implicit assumption that the coordinate system we were using would be the Cartesian system as in the XYZ system. But occasionally, it will be helpful. It will be helpful for us to work in other coordinate systems which operate with different variables. One such system is the cylindrical system and the other system is the spherical polar system. Now, why are we doing this? Let me give you a simple example to understand this thing. For instance, if you were to work with the electrostatic field, what is the property, the mathematical form of the electrostatic field? Q1, Q2, that is to say, product of the two charges. Let's not worry about two charges, let us worry about one charge. One charge, you've got one charge, you place it at the origin of coordinates. And what is the strength of the field produced by this charge? It is Q, that is the value of the charge, divided by 4 pi epsilon naught r squared into vector r cap. Now this is in the radial, in terms of the radial variable r. Suppose you were to write it in terms of the XYZ system, then what would you have written? You would have had to write Q divided by 4 pi epsilon naught. Instead of r squared in the denominator, you would have had to write x squared plus y squared plus z squared. And then the vector r cap, you would have had to decompose in terms of the unit vectors x cap, y cap, z cap in the Cartesian system. Immediately you realize that the formula loses its compactness. That's number one. And then you will have to take the divergence of this thing, the curl of all sorts of things, right? An integral of that. So it becomes a little difficult. I'm not saying wrong, but I'm saying mathematically it becomes more tedious and long-winded. Why not then just work with a coordinate system where the radial vector itself is a coordinate? And so such a system is the spherical polar coordinate system, where the three coordinates are theta, phi. Theta and phi are angles. We'll come to all those things later, but the electrostatic field does not depend on theta and phi. If they do not depend on theta and phi, then you just have to work with a single variable. Your differential equation becomes so much easier. Your mathematical task becomes so much easier. I'll just give you a simple example of that. Suppose you are on the surface, you are on the surface of the Earth and you are traveling everywhere on the Earth. And imagine that the Earth is a perfect sphere, which it is not. There is a slight bulge in the Earth's equator, along the Earth's equator, because of the Earth's rotation. But that bulge is a very small bulge. The Earth is not exactly a sphere, but it's an ellipsoid, a slight ellipsoid, small ellipsoid. Anywhere on the surface of the Earth, wherever you are, on the surface of the Earth, I'm not saying that, at sea level that is, I'm not saying that you're on top of Mount Everest or some high place, something like that. No, at the sea level, wherever you may be, the gravitational field that you will experience will be the same, almost the same. As I said, there will be a slight difference, but difference is a negligibly small difference. Small difference, I wouldn't say, at times that difference could be important. So what does it mean that to be anywhere on the surface of the Earth? Hello? Somebody's asked a question. Anywhere on the surface of the Earth, it does not matter what your latitude or longitude are. You can be in Delhi, you can be in Gandhinagar, you can be in Europe, or you can be in Australia, Northern Hemisphere, Southern Hemisphere, equator, you can be in the middle of the Indian Ocean, wherever you may be, you will still feel the same gravitational field. What does it mean? That the gravitational field does not depend on the latitude or the longitude, that is to say, other coordinates. Because if you have to specify somebody's position on the surface of the Earth, you have to specify coordinates also, such as the latitudes and the longitudes. But those things have no bearing on the gravitational force somebody may experience. Why? Because the gravitational force is simply a function of the radial vector, r. Okay, so that is the thing. So if you were to work with the Earth's gravitational field and try to understand its vector properties, then it will be helpful for you to work with the radial coordinate system or the polar coordinate system, in which the radial vector is a coordinate instead of working with the XYZ coordinate system. So sometimes, so these curvilinear coordinates that we are talking about, they are just for ease of our mathematical calculations. You can very well continue to work with the XYZ system, but the curvilinear coordinates can occasionally make your task easier. So that is why, and we shall discuss two such coordinate systems. One is the cylindrical coordinate system, and the other is the spherical polar coordinate system. The cylindrical coordinate system is the easier of the two to understand. Therefore, we shall start with that. But before I start, can you please confirm that you are able to hear me clearly? Because there has been some strange disturbance today, all sorts of. Can you please confirm? Please confirm that you can hear me clearly and
Yes,
see
sir.
the presentation. Okay, okay, thank you very much. Please mute your mic, everybody. Okay, so here, first let us try to understand the geometrical layout of the cylindrical system. Here we are. First, let us begin with our familiar XYZ coordinates. Here is the x-axis. It is drawn at an incline, but in actual fact, you must imagine it to be going towards you. You are looking at the screen right now, and the x-axis is directly pointing towards you. The y-axis is pointing to the right, and the z-axis is pointing to the top. All three axes start at the origin of coordinates O. Okay, fine. So I have asked you to come to this point P, which is suspended somewhere in three-dimensional space. Let us say if you're sitting in your room right now, it's, let's say, the ceiling fan, the rotating motor, the rotating part at the center, that block of your ceiling fan, whatever. So I have, maybe it's not working or something, you're trying to repair that. And so you'll have to put up a ladder and go to the ceiling fan and work like an electrician does. So how will you go? What are the coordinates of the point that is suspended in your room? So your room is a rectangular room, I believe. And so it has got three edges. One will be the x coordinate, the other will be the y coordinate, and the third, the vertical direction, will be in the z direction, the z coordinate. So if you have to go to this point P, now you follow carefully, step by step. Let us try to build this up and understand it carefully. From the vertex, that is to say, vertex of your room, that is to say, the origin of coordinates in your room, you shall start. Then you move along the x direction some way. Along one edge of the room, you move. Okay. Then, once you've come to this point, then from here, you move along this dotted line, this dotted straight line, which is parallel to the y-axis. So basically, you have traversed an x direction, now you have traversed an y direction. The point where the dotted y line ends will be at the foot of a perpendicular drop from P to the xy plane, here. Okay, so this point at the foot of the perpendicular from the position of the point P has got the coordinates x, y, 0. 0 meaning z coordinate is 0. On this plane, on this base plane, xy plane, The equation of the base plane xy plane is z is equal to 0. So you have x, y, 0. So those are the three coordinates for the foot of the perpendicular dropped from the point A. Okay, x, y, 0, you have it here. Now you plant your ladder here and you go up to the point P, or whatever the point P, as I said, could be a ceiling fan suspended from the ceiling, and you have to do your electrical work over there. So x, y, z. To come to P from the origin of coordinates O, you have had to take three paths. First is along the x direction, second is along the y direction, and the third is along the z direction. So three steps we have taken as per the Cartesian coordinate system to come to this point P. I hope you are clear on this diagrammatic understanding. But you will say, oh, well, I mean, what are you doing? I mean, you're taking some extra steps, X and Y. You have taken two, you have traversed two paths. Instead, if I am there beginning from the origin, the vertex of the room, instead of going through two steps or two directions, I can straight away make a shortcut from O to the bottom of this point P. This point P, O, I can travel along this path S here. So I have come from O to this point, and then from here, I go up. So basically, this second approach is a two-step approach. Starting from the origin of coordinates, I come along this way and come here. First step, then second step. I have carried out a shortcut, I have reduced a step, and I have had to walk less. Fine, that is very good, but then there is a slight problem with that. You still need, see, to come to this point, you would have had to be given two coordinates xy, two coordinate values xy. I will say that you have to go to the foot of the point P. And if you are an explorer or a map, scout, somebody like that, you'll say, fine, but you have to give me the coordinates of the foot of the perpendicular below the point P, which are x, y. Unless you give me that, how can I know where exactly to be? Every point on a plane is specified by two unique coordinate values. So on the xy plane, whose equation is z is equal to 0, any point will be described by two coordinates xy. 0 will be a fixed property of all points. 0 for z will be a fixed mathematical property for all points on the xy plane. Okay. So you say, okay, fine. I mean, I can start from the origin of coordinates, and then I can move out radially instead of going along x and y. I can start and I can move out radially from the origin to the foot of the perpendicular. Yes, but if I only say that starting from the origin of coordinates, you move out radially, let's say move radially out by 5 meters or so, or whatever. You'll say, yes, but 5 meters, I can move out radially by 5 meters, but in what direction? Because you can move 5 meters in this direction, in any direction you want. You can go 5 meters. And after having traveled 5 meters, you will end at a point. If you take the locus of all such points, which are obtained by traveling 5 meters in any direction from the origin of coordinates, then the locus of that point will be a circle. Basically, if I just give you one point of information saying that starting from the origin of coordinates, traverse a distance s, as in this. Now, let's not talk about 5 meters or 2 meters or whatever. Just talk in general terms. You traverse a distance s. You'll say, fine, I mean, I'll traverse a distance s, but you haven't given, since you've not given me the direction, I'll be anywhere on a circle whose radius is s. What to do? Then I shall have to give you more specific information. To come to this point, whose coordinates were earlier x, y, 0, you will have to traverse a distance s, starting from the origin of coordinates, a direct shortcut distance s, starting from the origin of coordinates. But this path s has to make an angle phi with respect to the x-axis. S makes an angle phi with respect to the x-axis. So if phi, let's say, without that value of phi, you will be uncertain as to where you are on a circle of radius s. Let's say if I say phi is equal to 0, you will just move a distance s along the x-axis. If I say phi is equal to 90 degrees, phi is equal to 0 on the x-axis, by the way. So you're starting your phi count from the x-axis and then go this way, anti-clockwise. That is the way angles are always measured. I hope you have not forgotten your school trigonometry lesson. And angles always start at 0 degree, then go anti-clockwise to 90 degrees, then again keep going anti-clockwise to 180 degrees, and like that it goes. So angles are not measured clockwise, angles are measured anti-clockwise. So starting from this axis, x-axis, it'll go all the way in an angle phi. Okay. If I say phi is equal to 90 degrees, you'll be there on the y-axis. So 90 degrees phi, starting from this is 0, this is 90 degrees. So there you are. You have traveled along this path, a distance is, making an angle of 90 degrees with respect to the x-axis. So unless I specify phi, you will not be able to reach your point precisely. So two coordinates must always be specified, whatever be the coordinate system you are choosing. If it is the xy system, the Cartesian system, you'll say your coordinates are xy, as in this and this. If it is the cylindrical system, your coordinates are s and phi, as in this and this phi. So, and of course, z continues to be 0. Thereafter, once you have reached this point, you go up this way, and your new, in terms of the new coordinate systems, s phi z, the point P will be described or pinpointed precisely by the coordinates s, phi, and z. This phi is known as the azimuthal angle. We shall, there are various other properties of phi and s. We shall now begin the discussion. But I would like to, before I move on to more detailed discussion, I'd like to point out something. Look at these coordinates that I have written. X has got a unit vector x cap, y has got a unit vector y cap, z has got a unit vector z cap. X, y, and z directions are frozen in space. If they are, x, y, and z coordinates are frozen in space. Therefore, their directions must also be fixed in space for all time to come. X will keep point, x cap will point in this direction, nothing will change that. And similarly for the y cap vector, unit vector, and the z cap unit vector. So from this point, if you go up, you will have a z cap unit vector in terms of both coordinate systems, xyz and syz. Z is a common coordinate in both the coordinate systems, xyz and syz. So from here, if you go up, you will have the z cap unit vector that is fixed. What about s and phi? Follow carefully. S cap is a unit vector that is aligned along this path described by the coordinate s, this horizontal, this hypotenuse. Hypotenuse of this right angle triangle, O to x, x to y, and then along this. So this is a right angle triangle, and S is the hypotenuse of that right angle triangle. So S cap is the unit vector along this radial outward path that you have. What about phi? Follow carefully. Phi is going from this, starting from the x-axis, and it goes in a circular anti-clockwise direction. That is the nature of all angle variables. Angles are not open-ended coordinates such as x, y, or z. X will start from 0, y will start from 0, and then in their respective directions, both x and y will go all the way to infinity. So they are open-ended. They can go all the way up to infinity. But the angle phi is not open-ended. Therefore, every time it completes a cycle, it resets the counter, the meter, like in a taxi. So what happens is that you start phi is equal to 0 here, then phi goes all the way around in a circular path and comes back here. So this 0 also coincides with 360 degrees after you've finished a full cycle, 360 degrees or 2 pi. Incidentally, now onwards, it would be better for you to think in terms of the radian variable. I'm sorry, the radian unit rather than degrees. Instead of thinking in terms of 360 degrees, you should think in terms of 2 pi. Instead of 90 degrees, you should think in terms of pi by 2, like that. It would be helpful for you to think now onwards in terms of radian units. So what about the phi coordinate? The phi coordinate, actually, you see this, follow what I'm trying to say carefully, listen to me attentively. This arc that I have drawn is a part of the arc that this point would have swept out in a circular motion. This point, the point where the path S ends, this is the point. If I were to sweep this point all the way around, it would have traced out a circumference of a circle, the circumference of a circle. This curve is a part of that circumference. Its phi is going along a circular direction, in a circular direction. So what is the unit vector phi? Unit vector phi is phi cap. Phi cap is tangential to this circular path. It is tangential to the circular path, whereas S cap is along the radial vector, which we are calling S here. S is starting from the origin of coordinates and it is going out. So it is along the radial vector. So this is along the radial, outward radial vector S, and this is tangential to the path traced out by this point as its path lies, as it lies on the circumference of a circle. So phi cap and S cap you have. One very important point about phi cap and S cap is that they are no longer fixed in space. X cap, Y cap, Z cap are frozen. These three directions are frozen in space, but S cap and phi cap are no longer fixed in space. Depending on the value of phi, S cap will change. If phi is 0, S cap will be pointing along the x-axis. If phi is 90 degrees, S cap will be pointing along the y-axis, like that. And similarly for phi cap, at this point, phi cap will be pointing this way. At this point on this line, phi cap would be pointing in the negative x direction. On the x-axis, phi cap will be pointing in the positive y direction because it will go like this all the way around. So those are two important points I wanted to make. First, that the value of S cap, the direction of the unit vector S cap will change. The magnitude of S cap is still 1 because unit vectors must come with the magnitude of 1 in any system that you have. Otherwise, you should not call them unit vectors. Unit means unit, which is related to unity, which is 1. And similarly, phi cap also has the magnitude of 1, the unit vector phi cap, that is, has the magnitude of 1, but its direction will also keep changing. So let us now look at certain properties, certain coordinate transformations as we go from one coordinate system to another. First, I have written a vector A, capital A, in terms of the Cartesian system. It will have an x component, a y component, and a z component. The x component will be a subscript x, x, y, z, x cap, plus a subscript y, x, y, z, y cap, plus a subscript z, x, y, z, z cap. So ax, ay, az are the three component magnitude of the three components, and they depend on the Cartesian coordinates x, y, z in the most general sense. It doesn't always have to be that ax will depend only on x. No, it can depend on y and z also. So to make the discussion most general, we are writing like that. Now this vector can also be represented in terms of the s, phi, z system. So for instance, if I were to talk about the radial vector on the xy plane, it will be along this direction. So that will be along, it will be x cap, vector x plus vector y. This will be vector x plus vector y. I can write it in terms of the vector s itself. We shall see how. But a vector that is represented in this three-dimensional space in terms of the xyz Cartesian coordinate system can very well be represented by the s phi z system with the same value. The vector itself on the left-hand side does not change. It has only got a magnitude and a direction. The components will change individually because the components can, so one component becomes large in the x system, another will have to be small, like that. So it's always the vector outcome will be the same. Okay, so let us now try to geometrically analyze this full discussion. First task will be, given three coordinates x, y, z, how will you transform them to a new set of coordinates s phi z? That is the question. You have been given three coordinates x, y, z. You will transform them to three new coordinates s phi z. If one set of values were to be supplied to you, then how will you find the other set of values? So let's see. Let us look at this diagram. This is s and this is phi. This is x and this is y. Therefore, x is equal to s cos phi and y is equal to s sin phi. X is s cos phi, this length, and y is s sin phi. If you look at these two equations here, on the right hand side here and here, you have been supplied the values of s and y. S and phi. On the right hand side, you've been supplied the values of s and phi in one coordinate system, and on the left hand side, using those two values, you are able to get x and y in terms of the old Cartesian coordinate system. The reverse is also true. If you are supplied x and y values, how will you find s and phi? Very simple. Here's the approach. S squared is equal to x squared plus y squared. I hope this is not a challenge to you. You can square this equation and this equation. You will get x squared is equal to s squared cos squared phi. And the second equation will be y squared is equal to s squared sine squared phi. And then when you add s squared cos squared phi plus s squared sine squared phi, you will get s squared. And that is equal to x squared plus y squared. Okay. And what about given y and x and y, you can find s. So can you also find phi? Yes, indeed you can. Here is y, here is x. So y divided by x is equal to tan phi. Tan phi is equal to y divided by x. Tan phi is equal to y divided by x. And then the last thing, z is equal to z. Well, z doesn't make any difference. The status of z in the Cartesian coordinates, that is x, y, z, is the same as the status of z in the cylindrical coordinate system, that is s phi z. So z is equal to z. So if you look at these formulae, three things here, z, the right hand sides give you values in the Cartesian coordinate system, which has x, y, and z, and the left hand side gives you values in the cylindrical system s, phi, and z. So if you know the Cartesian values, you'll be able to find the cylindrical values, and vice versa. If you know the cylindrical values s and phi, as you have over here, s and phi are given to you. If you know that, then you can immediately find x and y. Z, of course, is the same in Cartesian as well as cylindrical, so that's not a big challenge. Okay, so first task is for us to understand that given one set of coordinates x, y, z, how will you find the other set of coordinates s phi z, or vice versa? That is, given the set of coordinates s phi z, how will you find the coordinates x, y, z? Now the task is for us to find the unit vectors s cap and phi cap. First we have found the coordinates. Second task for us is to know what the unit vectors are like. Let's now proceed with that. The unit vectors could be found from this argument. Vector S is equal to vector X plus vector Y plus vector Z, which in this case is 0. Let us go back to the diagram. This is vector S, always lying on the plane Z is equal to 0. If Z is equal to 0, then Z does not contribute. So you will have vector S is equal to vector X plus vector Y by the law of the sum of vectors. That is what we write here. Okay, so vector S is equal to this thing. But then vector S can also be written as its own magnitude scalar S times its own unit vector S cap. S, vector S is equal to S into S cap, magnitude of S into unit vector S cap. So S cap is equal to vector S, and so unit vector S cap will be equal to vector S by magnitude of S. Now, what is vector S? Vector S is equal to X cap and plus Y cap. So when I substitute that over here, I will get X cap plus Y cap divided by S as a common factor in both. And what is X by S? X by S will be cos phi, Y by S will be equal to sin phi. So X by S is cos phi and Y by S is equal to sin phi. Basically, we are now transforming unit vectors. What are we doing here? First, what we have done as per this table and here also is given one set of Cartesian coordinates, how will you find the other set of coordinates? One set of coordinates in the Cartesian system, how will you find the coordinates in the new cylindrical system S phi Z? Or vice versa, if you're given the cylindrical values S phi Z, how will you find the values of the Cartesian coordinate? So that's the first thing. Second is that we have just had a discussion that the unit vector of S and the unit vector of phi will change direction, unlike the unit vectors of X, Y, and Z. So how is there a way, what is the formula to know the changing direction of both S and phi? That is what we are about to do now. Unit vector S cap is equal to cos phi X cap plus sin phi Y cap. And I've written something over here with a change of phi, the unit vector S cap changes direction on the Z is equal to 0 plane. We shall discuss that shortly. And the last one is quite easy, transforming unit vector Z. Sorry, just a minute. Transforming the unit vector Z is the same in the XYZ system and the SYZ system. That's the simplest thing you can do. It's a non-challenge really, it's a walkover. So Z cap is equal to Z cap. Z cap in the cylindrical system is equal to Z cap in the polar system and vice versa. But S cap is not. S cap is equal to cos phi X cap plus sin phi Y cap. Let us now look at this formula. Let us first just see how it changes. Suppose we shall put some values. Remember the formula cos phi X cap plus sin phi Y cap. And see what happens here. Let's go to the diagram. Cos phi X cap and sin phi Y cap. This S cap here is equal to cos phi X cap plus sin phi Y cap. So suppose phi is equal to 0. So cos phi will be equal to 1 and sin phi will be equal to 0. So if cos phi is equal to 1 and sin phi is equal to 0, then S cap will be equal to X cap. Just see in this formula, S cap will be equal to X cap. That is, when phi is equal to 0, this path will coincide with the x-axis and your unit vector will just be the X cap unit vector. Now when phi is equal to 90 degrees, cos phi will be 0 and sin phi will be 1. Therefore, S cap will be along the Y direction. That is what you have. So you can see I've just given you some simple examples, two very simple examples. You can apply all the other ideas and you can see that the unit vector S cap will keep changing direction depending on the value of phi. That is a matter of common sense, ought to be by now, so you shouldn't have any difficulty. So let us now look at what we are doing. We have found the unit vector S cap. If the unit vector X cap and Y cap are given and the angle of, the vector S is also given to angle made with the x-axis, by the vector S is also given to you. That angle is phi. Z, of course, is equal to Z, unit vectors, that is. Now what we shall do is that we shall try to find about phi cap. You follow the discussion carefully. Let us first go back to the previous diagram. How will you find phi cap? Let's look at this vector O as it is along this path S. You coincide, make phi is equal to 0 and you coincide it with the x-axis. Thereafter, you increase phi and this tip over here will trace out a circular path all around by the time you come back to where you started from. So what about the phi cap unit vector? Let us now see. It's a little, I mean, I hope you should have no difficulty understanding what is going on here. Let's see. Phi is measured with respect to the x-axis, as you can see in this diagram. So the unit vector S is, so we're just taking a vector of unit length, length 1, magnitude 1, and it has got a unit vector S cap. So when you have this angle phi, the unit vector is S1 cap. Then you shift this unit vector, trace it this way to point B. OA, earlier the unit vector of S was along OA. Now you have shifted this point, trace this point out through an angle delta phi to a new unit vector OB. OB is labeled by S2 cap. S1 cap is not the same as S2 cap. Be very careful about that because the value of phi has changed. Okay, if the value of phi has changed, then let us see how you can go about this whole business. You can do it algebraically. I mean, that's not difficult, but you can do it without too much of workout geometrically. First, let us look at this small triangle OAB. This triangle has got three arms of vector length S1 cap, delta S cap, and S2 cap. So S1 cap plus delta S cap is giving you S2 cap. That is by the law of addition of vectors, OA, OB. So applying the law of addition of vectors, this plus this gives you this. OA plus AB gives you AOB. So S2 unit vector is equal to S1 unit vector plus delta S cap unit vector. Okay. But then there is also another way of looking at it. This point and this point seem to be separated by a straight line delta S. But if I were to trace this path, then it would have gone along an arc length AB. Instead of a straight line AB, it would have gone along an arc length AB. Okay, so delta S cap. Now you follow. As you make delta phi go to 0, the curved arc length from AB will coincide with the straight path AB. So that is what it is. I'll discuss this thing in slightly greater detail in the supplementary set soon enough. But first, let us just follow this point. So the curved arc length will follow this track, AB. Okay, so delta S cap is this length. And as delta phi goes to 0, this straight length AB will become closer, will get closer and closer to the arc length AB. Now, I hope you are aware of a school trigonometric formula that the arc length is equal to the radial length multiplied by the angle through which the arc has been swept out. For instance, you write L is equal to r theta. You have a radial vector r. The radial vector r has traced out an angle theta. What is the arc length? If I call the arc length L, then you will say L is equal to r times theta. We are applying that principle over here. This is delta S cap in this direction. And this will be, the length of this vector is S1. I'm taking its magnitude times delta phi. And since it is going in this direction, Tangential to the circular path traced out, it will be phi in the phi cap direction. Delta S cap is equal to S1 cap delta phi cap, for delta phi is equal to 0. Okay, if that is so, then let's proceed with this discussion now. S1 cap has got a magnitude of 1 because it's a unit vector. Therefore, delta S cap is equal to delta phi cap. Okay. You divide this equation throughout by delta phi. Delta S cap by delta phi is equal to phi cap. And then when you are making delta phi go to 0, infinitesimally small, phi cap will be equal to ds cap d phi. If it is ds cap d phi, then what is S cap? S cap is given as cos phi x cap plus sin phi y cap. If that is so, take the derivative of that. Phi cap is equal to S cap depends on phi. X cap and y cap are constants, but phi is a variable. So you just take the derivative of phi, the derivative of S cap with respect to phi, and you'll have ds cap d phi is equal to minus sin phi. Derivative of cos is minus sin, and here you will have plus cos phi. So there you have the transformation of the unit vector of phi cap. Phi cap is equal to minus sin phi x cap plus cos phi y cap. That is, so these are the two unit vectors. Let us now apply this idea. Phi cap is equal to minus sin phi x cap plus cos phi y cap. What happens when phi is equal to 0? If phi is equal to 0, sin phi will be 0 and cos phi will be 1, and phi cap will be in the y direction. How so? Let us see how it happens. Here, phi is equal to 0, meaning you are on the x-axis. Phi cap will be perpendicular to the x-axis, pointing in the y direction, because it's a part of a circle that is being swept out all around. So here it will be perpendicular to the x-axis. Next is what happens when phi is equal to 90 degrees or pi by 2. So sine 90 degree will be 1, cos 90 degree will be 0. So phi cap will be minus x cap. How so? Phi cap will be minus x cap, meaning when you have swept your arc on this point, where phi is equal to 90 degrees, it is pointing in the opposite direction to the x-axis. It goes this way, and on this line, it is pointing that way. If that is so, then it's going in the minus x direction. That is the discussion about phi cap. It changes direction. Now what we shall do is that we have understood two things: how to transform coordinates from XYZ system to SYZ system or vice versa, how to find the varying unit vectors S cap and phi cap in terms of the unit vectors X cap and Y cap. That is done, that is given to you in these two boxes. S cap is equal to cos phi X cap plus sin phi Y cap, and phi cap is equal to minus sin phi X cap plus cos phi Y cap. That is done over here. Next task is, you would have noticed that I have written this vector and this vector. A is the same on the left hand side, except that the individual components have changed in the two coordinate systems. So the question is that if I were given one set of coordinates ax, one set of components, magnitude of components ax, ay, az, can I find the other set as, a phi, az, and vice versa? Here is the discussion. Let us now see. A is equal to as s cap plus a phi cap plus az z cap. Fine. Now what we shall do is that we shall substitute for the S cap with this formula, substitute for the phi cap with this formula, and Z cap remains unaffected as before. So this is AS, S cap, this is A phi cap, and the third is Z cap. Next task is for us to gather all common terms with the X cap unit vector and the y cap unit vector. As you can see in this formula, it is as cos phi minus a phi sin phi x cap. In this formula, it is as sin phi plus a phi cos phi y cap plus az. You can compare this formula with the vector represented in terms of the Cartesian coordinates ax, ay is Cartesian components ax, ay, az. If you do that, then this here will be equal to ax, this here will be equal to ay, and this is equal to az. So basically, you will be able to write ax is equal to as cos phi minus a phi sin phi. Ay is equal to as sin phi plus a phi cos phi. And both are az is equal to az. I'm leaving it as an exercise to you. You can check for yourselves that when you square these equations, ax squared is equal to this squared on the right hand side. Ay squared is equal to this whole thing squared on the right hand side. When you square these equations and add, you will get this. Ax squared plus ay squared on the left-hand side is equal to as squared plus a phi squared. And of course, to that, if you add az squared on this side and az squared on that side, the status of z is the same. You will get this formula. Ax squared plus ay squared plus az squared is equal to as squared plus a phi squared plus az squared. So my advice is that you square these two equations, you also square this equation, and you add all the three equations together, squared equations together, that is ax squared, ay squared, and az squared on the left-hand side will give you as squared plus a phi squared plus az squared, which is not very difficult to see. When you square this thing, what will you get? A squared cos squared phi plus a phi squared sin squared phi minus 2 a phi as cos phi sin phi. Similarly, when you have this thing, it will be a squared sin squared phi plus a phi squared cos squared phi plus a phi as sin phi cos phi. So a squared cos squared phi plus a squared sin squared phi will give you a squared. Similarly, a phi squared sin squared phi plus a phi squared cos squared phi will give you a phi squared. And then the mixed term minus 2as a phi sin phi cos phi and plus 2as a phi sin phi cos phi will cancel each other, and that will go away, and then you add az squared on both sides and you will get this quantity. So I've just given you a basic idea of this transformation of the components also. You can do it. I mean, there are many ways of doing it. I mean, maybe we'll be able to discuss a few of these things in the tutorials as well. But now I'm going to some important issues, which is about the line, surface, and volume elements in the Cartesian, in the cylindrical coordinate system. Remember, in the Cartesian coordinate system, the line, surface, and volume elements were dx x cap, line element is dx x cap plus dy y cap plus dz z cap. Whereas in the, and then the surface element was dx dy y cap, z cap, like that it goes on, dx dy z cap. So you have that. So here we shall try to see how those ideas, those things get affected, changed in the cylindrical coordinate system. Here, the line element is ds. First, let us try to have an understanding of this thing geometrically. For the sake of generality, I'm not keeping this figure confined to the xy plane. Here is x-axis, here is y-axis, here is z-axis. Whatever we are doing is suspended in mid-air somewhere above the xy plane. Okay, let us first see. You have started from the vertical axis z. If you had started on the xy plane, this point would have come down here at the origin of coordinates, but S in the more general sense is measured or is seen to begin from the z-axis, not from the point, should not be seen. It does emerge from the point on the on the xy plane. It does come out, look like it is coming out of the origin, but then if this thing is shifted up, It could be seen to come out from anywhere on the z-axis. So this is S, dn. Sorry, S has come up forward. So this is your starting point, this point. Then from here, you have taken a step forward, a small, infinitesimally small step forward, and the value of that step size is ds. From here you have started and you have gone some distance, ds along the S cap direction. Okay. Next is that, remember, what is the sequencing of coordinates? Be very clear on that particular point. In the Cartesian coordinate system, the sequencing of coordinates is x, y, z. In the cylindrical system, the sequencing of coordinates is s, phi, z. So, making a note of that the sequencing of coordinates is x, y, z, you say that the first step is along the x direction or x cap direction, the second step is along the y cap direction, and the third step is along the z cap direction. And similarly, in the new coordinate system, basically, you remember I have discussed it with you earlier also, label the coordinates, think of the coordinates as 1, 2, 3, coordinate 1, coordinate 2, coordinate 3. And so in the cylindrical system, the new coordinates are s, phi, z. So coordinate 1 is s, coordinate 2 is phi, coordinate 3 is z. Okay. So to return to the current discussion, you have to first make your move along the S cap direction. Starting from here, you are moving a path ds, small length ds, S cap. So that is the first component in your line element formula, ds, S cap. Second is S d phi. We have to be a little careful about this S d phi part. If this length is S and this angle is d phi, and you want to move to the new position defined by this green line, starting from here, you have swept and you have come here, S d phi. So this arc length will be S d phi. If this arc length is S d phi, then this arc length will be S plus ds, whole thing into d phi. But then when you break up, I mean, if you open the brackets, it will be like S ds plus ds, sorry, it will be like S d phi plus ds d phi. But ds d phi has got two d's. In the infinitesimal calculus, you just retain the first order in the limit of something going to 0. Therefore, this arc length, although it is looking greater than this arc length, now you try to understand the same argument in the English language rather than mathematical language. Although this arc length, outward face, it's like a swing, door swept out or something like that. This outward arc length looks greater than the inward arc length, and indeed it is. But when this distance ds goes to 0, if it is an infinitesimally small displacement ds along the s direction, if it is infinitesimally small, then this arc length will be nearly equal to this arc length with an infinitesimally small difference. Therefore, you can write the s d phi here. You can also write s d phi here. So let us now try to see. First, you have traveled along this length ds. Second, you have traveled along this path s d phi. And third, you will have to go up vertically along the z direction dz. So first path is, first line component of the line element is ds s cap. Second is s d phi. Now let us look at the component of s d phi, unit vector of s d phi. S d phi is a part of this curved path, which is a part of a circumference of this circumference of a circle. S d phi is going around like this thing, sweeping out a small length. It's a small length taken out of the circumference of a circle, S d phi. If that is so, then it is pointing in the phi cap direction. So S d phi is pointing in the phi cap direction, ds is pointing in the s cap direction, and z dz, which is the upward distance, this height would have been dz here. I've written over here, this height is dz. It's the same, this here and this here are the same. So this height dz is in the vertical direction z cap. This is the third line element. I hope you have not forgotten what I asked you to think of during the Cartesian discussion on the Cartesian coordinate system, dx, x cap, d plus dy, y cap plus dz, z cap. All you have to do is to treat this thing in the same way. This is 1, this is 2, and this is 3. So we shall now find the surface elements of this wedge-like thing that we have drawn. In the Cartesian coordinate system, we draw a little cuboid. Here we have drawn a part of a section of a part of a cake. So if you have a cake is like a birthday cake, let us say. Usually birthday cakes are cylindrical, like a circle, like a disc, thick. I mean, it's a thick disc. Although you can also have square birthday cakes, some cuboidal or cubic birthday cakes, but it's usually round. So you cut a sector out of the cake with your knife. So this is like that sector. And then out of that sector, you're cutting out a small section. The inner length of that section is S d phi. The outer length is slightly greater, but you still call it S d phi. This length is ds, and this height is dz. This is that small section that you have cut out of the sector of a cake. How many faces it has got? It has got 6 faces still. Let us see, a top face and a bottom face, which are the same. A left face and a right face, which are also the same. And then a back face and a front outer face. The front outer face is slightly larger than the inner back face. I hope you are able to understand that geometrically. However, since this length is very small, going to 0 nearly, the front outer face will be nearly equal to the back inner face. This face is a part of a cylinder now. It's a curved face. So first let us see what are the areas of these faces. The top face. The top face is between ds and, this is the top face. It's between the s cap unit vector and the phi cap unit vector. That is to say 1 cross 2, ds s cap cross s d phi phi cap. So it will be s ds d phi and then s cap cross phi cap. And that I'm writing as z cap. Why? I shall show you the proof later mathematically. I hope you have not forgotten that when you have the Cartesian unit vectors x cap, y cap, z cap, x cap cross y cap is equal to z cap because they are all mutually perpendicular. Similarly, y cap cross z cap is equal to x cap and z cap cross x cap is equal to y cap. I hope you have not forgotten that because they are mutually perpendicular. And so it is that these things are also mutually perpendicular. The diagram shows you that, although we shall establish it more formally later. This is s cap. This is phi cap, this is z cap, and they are all perpendicular to each other. So s cap cross phi cap will give you the third unit vector z cap. That is what you get, 1 cross 2 vector. Similarly, the open outer face. This is the open outer face. It's like a curved window, part of a cylinder, part of a cylindrical window. The open outer face is between phi and z, 2 cross 3, phi and z. So you will have s d phi phi cap cross dz z cap, 2 cross 3, s d phi phi cap dz z cap, and so it will be s d phi dz phi cap cross z cap. 2 cross 3 will give you 1, and so 2 is this, 3 is z, and 1 is s cap. So you will have s cap over here. And then the side face. The open outer face is very important, as you will see later. So please just make a note of this thing. And the side face is trapped between S and Z. That is to say 3 and 1. Side face is S and Z. You have to go in a cyclical order. 1, 2, 2, 3, 3, 1. Don't write 1, 3. 3, 1. So dz z cap crossed with ds s cap. dz ds z cap cross s cap. Z cap, when you cross it with S cap, you will get phi cap. That is again a unit vector. Okay, and what about the volume element? Just like in the XYZ system, I write dx x cap plus dy y cap plus dz z cap. The volume element is simply the scalar part of the three components dx, dy, dz. And so it is that here you have ds s d phi dz, ds s d phi dz, s ds d phi dz. This is volume element is a scalar. I've written something over here. I'm giving it to you as a food for thought. What happens when you integrate this thing? What happens when you integrate the open outer face? What is the volume of a cylinder? The volume of a cylinder is pi r squared, where r is the radius of the cylinder, times the height of the cylinder. Pi r squared is, r is the radius of the cylinder, pi r squared is the base area of the base of the cylinder, and h is the height of the cylinder. So the volume of the cylinder will be pi r squared into h. You can actually get that thing by integrating this little 3D carrying formula, SDS d phi dz. Well, we shall discuss that thing later in more detail. Anyway, so it's time nearly. I'd want to stop here. In the next class, we shall discuss this thing. That next, on Friday, we have Ganesh Puja holiday. I hope you're aware of that fact. So we don't have any class on Friday. We will have a class next Wednesday. But today, this afternoon, we have a tutorial from 2 to 3. Be there in the tutorial. You'll be supplied the tutorial sheet and the link in due course before 2 o'clock. Okay, so I'm stopping the sharing. If you have any question to ask, you may please do so. Otherwise, we may end. I'm anyway stopping the recording. Hello? Anybody has any question to ask? Nobody? I'm stopping the recording.